Hello and welcome to my talk. My name is Dinesh and today I'm going to be talking about systematic design of selectors for active constraint switching. Selector logic blocks, also commonly known as overrides, have been in use in the process industries for several decades to switch between a plurality of controllers, especially when the number of manipulated variables is less than the number of control variables. And selector logic blocks are available as a part of any standard digital control system software package that is used in the process industries. Despite their widespread use, not just in the process industries, but also in the other application domains, selectors are currently designed in an ad hoc fashion based on engineering know-how and experience. Selectors are introduced in various classical process control textbooks such as Shinsky, Seaborg and co-authors, Marlin, Wade, etc. And they are demonstrated using various illustrative examples. Currently, there is a lack of systematic procedure to design the selectors for active constraint switching that are actually verifiable by design. In this talk, we address this gap and provide a systematic design procedure which can be applied without the need for detailed process models. In particular, we will show the use of selectors for active constraint switching in the context of economic optimal operation. Often, optimal operation occurs when some of the constraints are at their limiting values. For example, when the market price for the product is high, then the process should be operated at maximum production capacity in order to maximize the profit. Now, constraints that are optimally at their limiting values are known as active constraints. And when some of the constraints are optimally active, the simplest approach is to control the constraints at their limits, possibly with some safety margins known as backoff. For example, in region 3 here, we have two constraints that are active. Then the optimal operation here happens when we control these two constraints to its limiting value. And when the price increases, we switch from region 3 to region 1. When the set of active constraints changes, then this requires a change in the control variables and reconfiguration of the control loops. This can be achieved by using selectors by designing independent controllers for each control variable, and we use a selector block such as a maximum or a minimum selector block to select between the maximum or minimum value of all the inputs computed by the different controllers. Let us look at a simple example to motivate why we need a systematic design procedure for designing the selector blocks. Now consider a gas turbine engine, say for example for power generation or for aircraft propulsion, and we have two manipulated variables, the air inflow rate and the fuel rate. Suppose the objective is to control the engine power to a desired set point subject to a maximum constraint on the rotational speed, a maximum constraint on the engine temperature, a minimum constraint on the engine pressure, and a minimum constraint on the air inlet pressure. And in addition, we have a max constraint on the fuel injection rate. Assuming that the air inflow rate is used to control the engine temperature TE, then we are left with one manipulated variable, namely the fuel injection rate, to achieve the other objectives. Firstly, it is not evident if these different constraints are consistent, and if not, under what conditions can we expect infeasibility. Secondly, in order to achieve optimal operation and switch between the different active constraint controllers, it is not clear if we should use a maximum selector block or a minimum selector block, or if we should use a combination of a max-min selector or a min-max selector in series. And finally, in the case of infeasibility, it is not clear how to design the selector blocks such that we can guarantee that the most important constraint remains feasible. We will now present a systematic procedure to design selectors for active constraint switching. Consider a process with a single input U and many potential control variables Y. Now we can have at most one CV constraint with a desired set point that may be given up if necessary. We can have any number of CV Yi with inequality constraints that may be optimally active. And we may in addition also have inequality constraints on the manipulated variable itself. Let us denote Gi to be the steady state gain from the input U to the output Yi. The first step is to divide the constraints into two subsets according to the following criteria. Y plus is a set of constraints where reducing the input is better in terms of satisfying the constraints. This means that for CVs where the gain gi from u to yi is negative, then the set y plus includes the corresponding minimum constraints. And for CVs where the gain gi from u to yi is positive, the set y plus includes the corresponding maximum constraints, and the set y plus also includes a possible max constraint on the MV. Similarly, y minus is a set of constraints where the increasing the input is better in terms of satisfying the constraints. This means for CVs where the gain from u to yi is negative, the set y minus includes the corresponding max constraints. And for CVs where the gain gi from u to yi is positive, the set y minus includes the corresponding minimum constraints. The set y minus also includes a possible minimum constraint on the MV. Let us define ui as the value of the input u, which at steady state satisfies the constraint yi lim. That means ui gives yi equals yi lim at steady state. Now let u bar be the largest allowed input u that satisfies all the constraints in the set y plus, and u underline denotes the smallest allowed input u that satisfies all the constraints in the set y minus. Then, to have feasible operation using u as a manipulated variable, we must at any given steady state operating point have u underline less than or equal to u bar. This is because we need u to be less than u bar to satisfy the constraints in y plus, and at the same time we also need u to be greater than u underline to satisfy the constraints in y minus. And satisfying both these conditions is possible if and only if u underline is less than or equal to u bar. This tells us that the constraints are feasible when we have an allowable operating window. And to get a unique value for the input u, we need to have another objective. Typically, this is a control variable which has a desired set point. In the case of economic optimization, the desired input denotes the value of the MV that minimizes some unconstrained optimization problem. Assuming feasible operation, in this case, the optimal input is given by a mid-selector. That is, if the unconstrained optimum u naught lies in the feasible region, then the optimum u star is equal to u naught. If u naught is infeasible, then the optimum occurs when u star is equal to u bar. And similarly, if u naught is feasible but on this side, then the optimum occurs when u star is equal to u underline. There are several ways where this can be implemented using selectors. The most obvious is with 3 selector blocks where we have a max and a min selector blocks to compute u underline and u bar for the constraints in y minus and y plus respectively, and we have a mid selector to switch between the 3 values. However, implementations with only 2 selector blocks are also possible where we use a max and a min structure in series or a min and a max structure in series. If the constraints are feasible, then all the structures are equivalent. However, when the constraints are not feasible, then the different structures behave differently, and it is important to understand how they behave in order to choose which structure to use. When we use selector blocks in series, the last selector block will always be satisfied. That is, in the max-min structure, the constraints y minus are masked and y plus will always be satisfied. Similarly, in the min-max structure, the constraints y plus are masked and y minus will always be satisfied. However, when using a mid-selector structure, we cannot say conclusively which of these constraints will always be feasible. Often, the different constraints have different levels of priority, and a common approach to handle infeasibility is to give up the less important constraints. And we can see that the order of the selector block plays an important role in deciding which constraints are given up and which constraints remain feasible when we have infeasibility. That is, when we have a constraint in y plus that is more important than a constraint in y minus, then we should use a max-min structure. And similarly, if we have a constraint in y minus that is more important than a constraint in y plus, then we should use a min-max structure. So to summarize the systematic design procedure, the first step is to group the list of constraints into 2 sets, namely the set y plus and the set y minus, depending on whether increasing or decreasing the input is better in terms of satisfying the constraints. Then we design individual single input, single output controllers to compute the input for each CV constraint and for the CV setpoint controller U0. Then we use a minimum selector block to choose the largest allowed input U bar that satisfies all the constraints in the set Y plus, and use a maximum selector block to choose the smallest allowed input U underline that satisfies all the constraints in the set Y minus. And we can say that the problem is feasible if U bar is always greater than or equal to U underline. If the problem is feasible, then we can achieve optimal operation by using a mid selector, where U0 is the control input computed by the controller that controls the CV with a set point that can be given up. And in the case of infeasibility, we can handle infeasibility by using a maximum structure if the constraints in Y minus can be given up, or we can use a min-max structure if the constraints in Y plus can be given up. Let us revisit the same gas turbine example and start by grouping the constraints into Y plus and Y minus. To do this, we don't need to know detailed process models, but we only need to know the sign of the steady state process gain from the input U to the different CV constraints. Then we can design individual single input, single output controllers and use a minimum selector block to switch between the controllers that are in Y plus and use a maximum selector block to switch between the controllers in Y minus. And by using a max-min selector in series, we can say that in the case of infeasibility, the constraints in Y plus will remain feasible and the constraints in Y minus will be given up. That is, in the case of infeasibility, the minimum constraint on the engine pressure will be given up. Due to imperfect control or measurement noise, sometimes it may be desirable to add a safety margin known as backoff, where the set point is offset by a constant value from its limit. In order to quantify the loss due to backoff, we can consider this optimization problem and analyze the sensitivity of this optimization problem with respect to this backoff parameter epsilon. And if we do that, we can show that the loss is directly proportional to the Lagrange multiplier lambda star, which is the Lagrange multiplier of this constraint. The main implications of this for control structure design are: firstly, we can determine which CVs need to be tightly controlled. That is, if the Lagrange multiplier for a given constraint is large, then this constraint must be controlled tightly in order to minimize the losses. Secondly, we can decide if we can simplify the control structure design. For example, if the Lagrange multiplier for a given constraint is sufficiently small such that the loss is negligible or acceptable, then one can allow a large backoff, thus simplifying the control structure design. When using selectors, only one of the control actions computed by the different controllers is implemented on the plant at any given time. This means that for the controllers that are not selected, the feedback loop is broken and the integral term may build up, leading to wind-up issues. This wind-up can be avoided by using the back calculation scheme, where the additional feedback path is generated by using the difference between the output of the controller UI and the actual output U implemented on the plant. This signal is then fed back to the integrator with gain KAW, known as the anti-wind-up gain, such that this error goes to 0 when the controller is not selected. Here, the anti-wind-up gain is a tuning parameter, and a large value of the anti-wind-up gain means that UI is going to be close to U. A too large value of the anti-wind-up gain may also activate UI when it is not necessary. Therefore, a reasonable value for the anti-wind-up gain to avoid unnecessary activation for small changes in YI or in the set point for YI is given by the integral gain divided by the proportional gain. So far, we have considered an important case where all the constraints can be associated with a single manipulated variable U. In this case, it was possible to divide the constraints into the sets Y plus and Y minus, which can be associated with minimum and maximum selectors respectively. In the case of multiple inputs, we can then apply the systematic design procedure if each MV is paired with a set of constraints a priori. Then for each MV, we can divide these constraints into two subsets, YU plus and YU minus, and similarly for the MV V, we can divide it into YV plus and YV minus and apply the systematic design procedure. Now, if for a given MVU, we have hard constraints in both y plus and y minus, and in the case of infeasibility, we can control one hard constraint using U, and we give up controlling another constraint depending on whether we have used a min-max or a max-min structure. In this case, we don't necessarily have to give up controlling the other constraint because we can find another MV to take over the hard constraint that is given up by the MVU. Now, this can be achieved by using MV-MV switching, say for example, by using split range control or valve position control. In large multivariable systems with a lot of such CV-CV, CV-MV, and MV-MV switchings, the control structure can quickly become complex, and perhaps one would then be better off with multivariable controllers such as model predictive control. Now, on that note, I would like to end my talk, and thank you for your attention.